Okay. Okay, so welcome everyone. This is going to be our last online seminar for this year, and it's a pleasure to introduce today's speaker, Sandro Donadi. Sandro is an expert in collapse models, and he did his PhD in Trieste in the research group of Angelo Bassi. After that, he had postdoctoral positions where he worked on foundations of quantum mechanics and with a particular focus on collapse models, in particular in respect with their dissipations and the radiation effects. More recently, I think he's also is also working on classical gravity models to describe how gravity interacts with quantum systems. And currently, he's at the University of Palermo, working with Rosario Lofranco. So, said that, Sandro, the floor is yours. You can
Okay.
start.
Okay, thank you, Martin, Dennis, and thank you to everyone also to be here. It's a pleasure for me. And so I will discuss mostly about Diósi Penrose model. I will start by giving some introduction. I don't know how many of you are probably already familiar, but maybe some are less. So I still left some slide of introduction of a model, and then how this model can be tested. And towards the end of the talk, I will discuss about this other proposal to test the nature of gravity measuring diffusive effect. Anyway, I will start. And again, thank you very much for this opportunity. Okay, as usual, I start most of my talk with this slide on the measurement problem because collapse model in general, and Diósi Penrose is one specific collapse model, were introduced to solve the measurement problem, which arises because in the standard formulation of quantum theory, we have these two different dynamics for the state vector. On one hand, you have the Schrödinger equation, which is linear and deterministic, and then you have the collapse, which is nonlinear and stochastic. But the theory does not tell clearly and in a not ambiguous way when you're supposed to use one dynamic or the other one. And for example, this was stressed by many people, also Einstein, Schrödinger, and John Bell. And here, John Bell, in this quote, he asked what qualifies some system to play the role of measurer. And so out of possible, there are different way out to solve the measurement problem. And the approach taken by collapse model in general, and so also by Diósi Penrose model, is to modify the Schrödinger equation and add by adding some term which essentially describe a wave function collapse. So these two separate dynamics, they go together in a single unique equation. And of course, there are some constraints that these new dynamics must fulfill. The first one is that for small system, you need to recover Schrödinger evolution almost completely because we know that small system manifest quantum behavior. On the other hand, this new term that you added to describe the collapse needs to become dominant when you have a large system, and all this needs to happen automatically because of the equation, not because you choose to call some system measurement device or not. Otherwise, you will not solve the problem. And regarding this new term that one has to add, they need to be nonlinear, otherwise you don't have collapse. But then, once you add nonlinearity to a Schrödinger equation, in general, you may end up with some issue, especially with regards to possibility of doing faster than light signaling. When you consider, for example, setup like the one using Bell experiment, like EPR-like setup. And so, in addition to nonlinearity, you also need to introduce some stochasticity in such a way that these dynamics, despite being nonlinear, it cannot be used to do faster than light signaling. And this is the way how the structure of collapse model is built. Now we go to Diósi model. Also Diósi is here. Hi, hi, Lajos. So we introduce Diósi model, which was suggested by Lajos Diósi in 1989. And in this model, this is an example of a collapse model equation where essentially the dynamics of the state vector contains the usual Schrödinger part, and then you have this other term which describe a collapse, which is related to gravity. The relation here with gravity is given by the fact that the coupling of the collapse is the gravitational constant, and that the correlation of this Wiener process is essentially of the form of a Newtonian potential. Also, the collapse is happening is driven by this mass density operator, which, when you move to first quantization, essentially means that you have a collapse in space. As you can see in these red terms, we have both the feature I mentioned before, because we have the nonlinearities, which are in these terms. This bracket means the expectation value of the operator computed on the state at time t. And we have a stochasticity, which comes from the Wiener processes. And given this equation for the state vector, one can compute the corresponding master equation, which is of a Limblad form, because the dynamic is Markovian, precisely because these terms are given by Wiener process. So overall, the overall dynamic is Markovian. And so we see that in addition to the von Neumann term, we have some term describing collapse in position. And a way to quantify the strength of this collapse is to, if for a moment you neglect the free evolution, you just focus on the second term, and then you check how matrix element evolve in time. Here, A and B are two different position eigenstate. And so one can see that the off-diagonal element essentially have a decay in time, which is of this form, where the time of decay is given by this double integral. This is essentially this at a master level at the level of a master equation, it shows the effect of the collapse, which is essentially to diagonalize the density matrix in the positional representation. Now, after this model proposed by Diósi, a few years later, there was also Penrose who proposed that essentially there is a deep incompatibility between general relativity and the quantum superposition principle. And so that whenever there is a system which is set in a superposition of two locations, like A plus B, essentially some mechanism has to enter to collapse this superposition. So Penrose does not provide a full equation like Diósi, but it still provide a way to compute the to estimate to compute the time of decay of a superposition of this kind. So typical superposition here plus there, and how this depends on the mass of the object. And the approach he used is the following. So moving to essentially the initial arguments start from general relativistic consideration, and in particular on a tension between equivalence principle and superposition principle. And the way to see this at a non-relativistic level is imagine that you have some mass which shows some gravitational field, and this mass is in this superposition. And now you put a test mass in this point R. Well, then, if because the mass is in a superposition, it should also generate a superposition of different acceleration on this probe. So I will have the probe in a superposition of being accelerated according to GA and being accelerated according to GB. And here the contrast with equivalence principle is that I cannot find a reference frame where I can, by making a change of coordinate, cancel at the same time GA and also GB, exactly because there is not a single acceleration. And the way that Penrose suggests to compute the, so here I have two different configuration, A and B, which essentially lead to these two different acceleration. And so a way to estimate the difference in terms of an energy of these two configuration is to take the difference of that acceleration that I have when the source mass is placed in A minus the one when the source mass is in B, and then I take a square because I don't want that to have cancellation effect, because sometimes this difference is positive and sometimes it's negative. So I'm interested in the module, so I take the square. And then I add over all possible point in space because I mean, yeah, I pick up with this R, but this point is not more special than other point. And then okay, you need to add 1 over G for dimensional reason, and you get something which has the dimension of an energy. And the point of Penrose is that a superposition which is associated to this delta E will collapse in a time which is exactly equal to some tau, which is h bar divided by this delta E. And now you can show in few steps that this formula can be rewritten in this form in terms again of the mass density, and this is essentially the same formula that we saw in the slide before for the Diósi model, apart for some factor 8 pi. So this is the reason why these two proposals, despite they've been derived from different, starting from different idea, but they've been then later in the literature also considered as a unique model, Diósi-Penrose model, because they predict for a superposition here plus there essentially the same time of decay. And as I told, Penrose suggests that the time of decay is of order of h bar over delta E, and this is essentially the same one predicted by the Diósi model. And now one can try to give an estimation to understand how strong is this effect. And one, for example, can replace the mass density with the one of a proton, and then you find out that the time it takes for a proton in a superposition here plus that to decay is of order of millions of years. And this is good and consistent with the fact that when we do interferometric experiment with protons, for example, we can see interference effect because the collapse is essentially not effective. On the other hand, if you consider a macroscopic system, but not even huge, like in this example, I took a grain of dust of order of 10 micrometer. So then the collapse time, if you imagine that in some way you manage to set this dust grain in a superposition, then this superposition will collapse in 10 to the power minus 8 seconds, so almost instantaneously. And so this shows how the model somehow is good in solving the measurement problem because microscopic systems are essentially not affected by this collapse effect, but the system which are in the macroscopic realm, they collapse essentially instantaneously. Now, there is an important point that in the original model, if you take the formula I showed before for that with that double integral, essentially you can see that if you take a mass density which is point-like, so like Dirac delta, then the integral diverges, essentially because there is this Newtonian potential which diverges in zero. And so you need to introduce some extension for this mass density as a cutoff. And for this, there has been two different proposals. Originally, Diósi suggested to take a cutoff at the order of femtometer. Also, I think in the spirit that we are working at a non-relativistic level, so to start to go to lengths which are smaller than 10 to the power minus 15 meter, then you're not anymore dealing with things in non-relativistic energies. Well, Penrose suggested to relate R0, so the mass density, with the modular square of psi. Now, what it was shown by Grassi, and Rimini in 1990 is that The choice at zero is essentially incompatible with what we observe because, as I'm going to discuss more in detail in the next slide, uh, what spontaneous collapse does, in addition to collapsing superposition, is to induce some diffusive effect on the system. And this diffusive effect manifests in many ways, one of which is heating of the system. And when you take at zero so small, this at zero small means that the effect of a collapse is stronger. This would predict an heating that is not compatible with what we observe. Okay, I basically already anticipated a bit what I'm telling in this slide, but because this collapse model in general, and for sure also the Penrose model, they modify quantum mechanics. So these models are not just an interpretation of quantum theory, and they can be tested. And then to test, you can think about two classes of experiment, the interferometric experiment and the non-interferometric one. The interferometric, essentially they look for the loss of coherence, which we know is bad because the equation have been built in such a way to destroy superposition. But as I told, another effect of the presence of collapse is to induce diffusive effect. If you want, this can be understood when you look at the master equation of a Diósi-Penrose model. One of the effects of the Limblad term is exactly to introduce some form of heating. And the crucial point is that these diffusive effects are always there, even when you have a well-localized system. So it's not that they are there only when you put a system in a superposition, while when it's well localized, you don't see them. They are always present. And so this allows to test the model without the need of setting system in macroscopic superposition. So a possible way to test whether the spontaneous collapse is there or not is by measuring this diffusive effect. Now, specifically for the Diósi-Penrose model, this has been done. This distinction between interferometric and non-interferometric text lead to different proposals. The first one was a famous paper from Marshall, Penrose, and collaborator from 2003, using optomechanical devices. Then more recently there was a proposal in 2019 again from Penrose and with Fuentes and all on using BEC. And it was also considered the possibility of doing experiment maybe in space where there is no gravity, so you can do interferometric experiment more easily. But the problem again is that in all this approach, I mean, the idea in principle are good, but it's still these are experiments still very hard to be performed. While the non-interferometric test, as I told, they do not require the creation of large superposition, and so one can try to use this the detection of motion of system with high precision to set bound on the Diósi-Penrose model. This was done, for example, by studying the laser pathfinder or the spontaneous eating more recently by Vinant and Hulbrick. But another effect, which is a direct consequence of this spontaneous eating, is radiation emission. Essentially, here the intuition is the following: that collapse induce this Brownian-like motion on your system exactly because collapse is random, and so your system it is as if there was an external Brownian motion shaking it, and when a system is charged and is shaken, then this will emit radiation. This is according also to classical physics intuition, because this Brownian motion will accelerate the particle. And so protons and electrons within atom will emit radiation, will emit photon exactly because of this noise induced by the spontaneous collapse. Turn out that this effect of radiation emission is one of the most powerful to test this kind of model. Now, I'm not going too much in the detail of this calculation because then I want to discuss also about other stuff, but just to give an outline, the way the object that one computes theoretically, that we want computed is this radiation emission rate, where the central quantity to compute is the number of photons emitted at a certain time with a given wavelength and polarization. And this can be done in several ways. In this article, we use the approach of using the adjoint master equation. There are actually much simpler approaches. But the idea is essentially to start from this master equation where all these terms include the effect of Diósi Penrose, this Limbladian. It's just the same one as before, but written for many particles and in a different form. While the H also is not as simple as it may seem because it includes the system, the electromagnetic free field, and the interaction between system and electromagnetic field. So calculation can be done perturbatively with respect to the Limbladian, with respect to the collapse, and with respect to the electromagnetic interaction. And essentially, at the end, one arrives to a formula which is this one, uh, which I highlight in this red box. Uh, so this is the formula for the radiation emission from a crystal where we have Na atom. As expected, the emission is proportional to the number of atoms involved, while is it proportional to the square of the atomic number of an atom. And this is due to the fact, and I will discuss this better in detail in the next slide, but essentially this n square comes from the emission of the protons. Because protons are all confined in a very small region within atom of order of femtometer, then what happens is that when this collapse happens, it shakes all proton in the same way, and because they are also very nearby, they emit coherently, and this coherent emission manifests in an amplification of order n square, in contrast to incoherent emission, which is only linear will be only linear in n. And then, okay, we have other constant, and we have that the emission rate, it goes as 1 over the frequency. So omega k is the frequency of the emitted photon, and so the emission rate goes as 1 over omega. This is a general feature, at least for as long as one considers sufficiently high energy photon, and by high energy I mean in this range of energies, which is essentially the energy of gamma rays. And more importantly, this is happening because we are considering a Markovian model. There are, in principle, one could also consider to extend the model to introducing a Markovian effect, and then you would have that the emission rate would be proportional to the spectrum. Also yet you will get basically a factor which is proportional to the spectrum of the noise inducing the collapse. And finally, we have R0, which is that parameter I introduced before, this mass extension of the mass density, and which entered as 1 over R0 to a power cube. So, as usual, small R0 means collapse is stronger and means you emit more, you have a larger emission of photons. Okay, just briefly, I was mentioning before that the most clever way to do the calculation when using the whole master equation, and one is this one. What one can do is to build a Schrödinger equation by taking the standard Hamiltonian, this H, which include the electromagnetic field and system, and then adding a potential which mimic the effect of a collapse. Of course, when I say mimic the effect of a collapse, I mean that clearly this is not a collapse equation. This is a standard Schrödinger equation. But as long as we are interested in computing expectation value of average quantities, this equation leads to the same master equation as the original Diósi-Penrose model, and so it can be used. Specifically, the form of this V, okay, here I reported it for also for the CSL model, but okay, we are more interested in DP here. So it has this form where these psi are noises which are delta correlated in time and with the correlation 1 over x. So uh, one in principle can use this Schrödinger equation and, for example, apply perturbation theory here using Dyson expansion, or one can do even something simpler, which is to consider this potential and then the classical potential. So I remove the hat, I compute the acceleration associated to this potential, and given the acceleration, essentially use Larmor formula, and with this we can compute the total power emitted, and we can relate it to the radiation emission rate, and you get exactly the same result that you get doing the fully quantum mechanical calculation. So this really confirms with calculation that this effect is of radiation emission is essentially classical. You can indeed find the right answer even doing a classical calculation. Okay, now I move to the experiment we did. So this was all about how to compute the expected radiation emission in Diósi Penrose model. Once you have the theoretical result, we gave it to our colleague in Frascati and Gran Sasso. The experiment was done in Gran Sasso, so Christian Piscicchia, Caterina Culceano, and Matthias Lauberstein. The setup was a crystal of germanium of approximately 1 or 2 kilo of that order. And so this is the crystal is this one green, and then there are several layers of material which further shield it. And here we had the data from the experiment where once you remove a background, which is this green line, essentially you're left with 70 photon emitted in 2 months. So the emission rate was really very, very low. And this allowed to set a very good bound on this parameter at zero. And in particular, this bound turned out to be 3 orders of magnitude better than the previous one. And it also ruled out the value, the proposal of Penrose for the value of R0, which was too related to the modulus square of the psi. And to conclude on the experimental side, this bound with this kind of experiment has been recently also improved by Majorano collaboration first. And even more recently, this is not yet published in journal, but is on archive by Xenon collaboration. Here also Catalina and Christian work on this. And they gain essentially 1 order of magnitude better on the bound of the model. Okay, so this was about bounds coming from experiment on this parameter at zero. And so in general experiment, what they can do, they can always set only upper bound on the strength of the collapse, which, okay, in the case of Diósi Penrose model, result in lower bound on this at zero. And then one can wonder, okay, but how long you want go on with by setting bound, whether is there any limit? Well, there is a limit, and the limit is that you introduce collapse model because you want to be sure that macroscopic superposition collapse efficiently. So if essentially, if you can prove that the strength of your collapse is so weak that even a cat will survive for several seconds in a superposition of being alive and dead, then your collapse model is essentially become useless. So one can set lower bound also on the strength of the collapse by requiring that a macroscopic system has to be well localized. Now, this creates there is some ambiguity in setting this lower bound on the strength of the collapse, which essentially, for our discussion about the parameter at zero, correspond to set upper bound on that zero. There is a bit of ambiguity because, actually, I would say not just a bit. What does it mean macroscopic? And what does it mean fast enough? So, in contrast to bound from experiment, which are sharp and clear, here there is arbitrarity in what to call macroscopic and what do you mean by long or short time. So a choice that has been used already for other collapse model like CSL model was to consider what happened to a graphene plate, which essentially with a size of order of 25 micrometer, and the requirement in this case will be that this graphene plate should collapse within 0.01 second when placed in a superposition clearly of distinct position. So here we take the distance of superposition d to be at least, for example, 4 times the size of the crystal. So um, now, why these numbers? Essentially, this L is the smallest possible length that can be perceived by human eye, while this tau is the human perception time. And here is the part where I say that there is a lot of arbitrarity because why human eye in particular is just a way to set some limit essentially to set some benchmark. But if for the moment, and then I will discuss possible variation of this choice, but for the moment, if you just take as good this choice of this graphene disk, as it was done also for CSL, well, then what you find out is that, strictly speaking, if you want this graphene disk to collapse within 0.01 second, which is so in this graph, we have L0 on the x-axis and the time of collapse on the y. Essentially, if you require the collapse to be fast enough for having the tau smaller than the red line, which is this 0.01 second, this is not happening in the Diósi Penrose for any value of zero, essentially, which is allowed, and the one in the gray area has been already excluded by experiment. Okay, then one can wonder, okay, how large should be this disk in order to have a collapse of Diósi Penrose model strong enough to collapse it efficiently? Well, you essentially need to get to this L of order of 246 micrometer, which is almost millimeter size. Then the line you see is this purple, which goes below this bound. And also, in case you change the distance of a superposition, that does not change much things because essentially, after some distance, the strength of a collapse saturates. So you don't gain much by increasing the distance. However, one can also wonder, okay, let's not get fixated with this plate. Let's consider, for example, a three-dimensional object. So again, in a superposition here, plus very well distinct. So D is much larger than L, is, for example, 4 times L. And then we ask how fast this can collapse. Of course, here the effect of collapse is much stronger because the system being three-dimensional, there is much more mass. And so overall, and also there are much more many atoms, one close to each other. And when you see the formula that gives you the collapse rate, essentially, this is sensible. It matters to have many atoms, one close to each other. And indeed, what one can find if one consider a cube is that essentially for already a cube of size of 1 micrometer, Diósi Penrose model collapse it efficiently for L0 between the current experimental bound and 10 to the power 4 Armstrong. Or if you take a cube of the size of 10 micrometer, essentially you can reach up to 10 to the power 7 Armstrong, which means millimeter size. So in general, if I had to, as I said, these upper bound are not very sharp. There is a lot of arbitrariness, but I will say that at least one can say that a reasonable bound, considering also a system like this, it can be to set R0 should be smaller than centimeter. So for R0 larger than 1 centimeter, then you really have that even a cube of the size of 10 micrometer will not collapse fast enough. Okay, now another recent development on the subject of radiation emission is the following. What we found out is that in the experiment I showed before, we always considered radiation emission from of of photons with energy of order of gamma rays, so high energy photon. What happens when you start to lower the energy of a photon? Well, some things interesting happens, and this is what we studied recently with Christian Peschick and collaborator. And essentially, the emitted spectrum is not anymore of a simple form of 1 over omega that I showed before in the red box, but the shape depends on the kind of atom which are emitting and on the specific model. And to understand why this is happening, it's useful to understand how this emission works, and this can be done in a very classical term, so it's kind of intuitive. The situation is the following. Imagine that you have a noise which shaken two particles. In this case, is the collapse noise. And for Diósi Penrose model, as well as also for CSL, within an atom, the noise are always correlated, essentially because at 0 and at C, they have been set bound on this parameter much larger than the atomic size. So now, given these two particles, which have been which are shaken by a noise which is correlated, there can be two cases. So, in one case, which is the case when you have coherent emission, you consider the wavelength lambda of the photon emitted much larger than the distance between these two atoms. Here I forgot to put, but this d is the distance between these two. And then what happens when these two charges are of the same kind? Then essentially the field, the way emitted by the first one, because the wavelength is much larger than the distance, add almost perfectly with the one close nearby, and so the total electric field becomes two times the electric field of one, and because the rate of emission is proportional to the intensity of the field, you get a factor 4. I mean, here is a factor 4 because I have two particles. If I was having n particle, I will get a factor n squared. And this is exactly the coherent emission I was talking about before for proton inside the nucleus. On the other hand, if I have opposite charges, and again I'm in the situation when the wavelength is much larger than the distance, then the emission of the first particle cancel almost perfectly with the emission from the second, and so overall the emission get suppressed. So the idea is that whenever I'm in the condition for coherent emission, the two system, the system emits in such a way as if it was a single particle with a charge which is the sum of the charges of a constituent. This is also the reason why, for example, if I consider a lambda which is way larger than the atomic size, then I have a high suppression of the radiation emission because all the emission from proton is cancelled the by the one of the electron. The other limit is when essentially now these two particles are much more distant compared to the wavelength emitted. And then what in general the module square is given by this formula. But when you compute essentially the overall emitted field and you integrate over the solid angle, essentially these terms with the field emitted from one particle and the one from another one average to 0. And so you get that the emission of the two particles adds incoherently. I just get the emission from the first one plus the emission. Here, this is the electric field, but essentially the emission rate is proportional to the square of the electric field. So the particles essentially emit independently. And so when I look what happened in an atom, essentially, again, following this classical picture, what I had is that as long as we were looking for photons um, with very small wavelength compared to the atomic size, essentially only the protons were emitting coherently within the nuclei, but then the emission of all electrons were incoherent and among themselves and also among with the nuclei. But if I start to look what happened for wavelength, which are a bit larger, so for a bit lower energy, like this green wave, then what I have is that these two electrons, that before they were emitting independently, now they start to emit coherently. And so the shape of the spectrum changes. And then if I take an even larger uh, wavelength, then the emission of these three electrons is also coherent and it tends to cancel even more the one from the nuclei. And essentially we did this kind of analysis, and what we found out is that the emission, for example, in CSL and DP model, has different behavior. So this one in blue in this graph is the behavior for high energy photon, the one that was studied till now, and the shape is always 1 over E, 1 over E, is the same formula that I showed before. But when you instead keep into, you start to go to lower energy, essentially this effect of coherent and incoherent emission become complicated and it depends on the energy level. And indeed, we see that even within the same DP or CSL model, if I use different atom, here is xenon, here is germanium, the spectrum changes. And even if I use the same atom but different models, the spectrum changes. So this is a new feature that we found out. How much time? Oof, sorry, it's taking a bit longer than I expected. Just one last word about this testing of collapse model using this diffusive effect. Essentially, we show that in DP model, CSL, you have this radiation emission, you have this diffusive effect. One can wonder, is this something unavoidable or is just specific of this model because we, after all, we put it by hand by adding this term with binary processes. And well, we have a result in this respect that as long as you want any collapse dynamics which collapses in space and is space translational covariant and does not allow to do signaling, then necessarily you have some diffusion in momentum, so some increase of delta p. So this is not just an effect related to this specific model. It seems that whenever you want to describe collapse, dynamically, then you have this diffusive effect. They are kind of unavoidable, unless you don't want to give up to one or two. Okay, this was a slide about some other proposal we did on possible test in space, and I added this also thinking about the meeting we had in Bremen, but maybe I just move forward the other topic now because otherwise I'm getting late. Also in this respect, there is also the current proposal of request using cold atoms. So in general, the overall idea is that going in space can be useful because there you can have a free time evolution of order of 100 seconds, and this may allow to do both interferometric and non-interferometric experiment more efficient. Now, about the last part of the talk, which is about this idea of probing the quantum nature of gravity. Since 2018, I think, or 17, there was this proposal by Bose and collaborator and Marletto and Vedral to essentially put two systems in a superposition, in a spatial superposition, and if they interact only gravitationally, initially they are in a separate state. If the final state is entangled, then this would be considered as a proof of a quantum nature of gravity. Also on this there is some debate on the definition of quantum and classical, but what is meant here is that gravity is not represented by an LOCC because, of course, if it was an LOCC, you will not see entanglement at the end. On a practical level, the challenge in this kind of experiment is that because gravity is weak, you need to put masses, even being very optimistic, of order of 10 to the power 13 AMU atomic mass in superposition, and this is very challenging. So what we suggested recently in this work was to change approach somehow and to exploit this chain of logic. That what is shown is that if gravity is classical, then it has to come together with collapse of wave function, and then collapse in space, and then this collapse in space, like what happened in collapse model, comes together with some decoherence and diffusive effects. And so one can essentially look for diffusive effect, and a possible setup of it we consider is of this kind. This is essentially two harmonic oscillator placed far away, so one can treat gravity as linearized gravity. Okay, this is another picture of a setup a bit more beautiful. What we had in mind were, for example, two torsion pendulum. And then the dynamics will be of this form where essentially, okay, you have the free Hamiltonian, this which is the Newton term linearized, and then you know that because of gravity is classical, there is some diffuse, some decoherence term, which in this kind of a setup can be modeled because you can linearize everything, and so can be modeled as something of this form, where this R is essentially all the possible quadratures. So if I have these two systems, RE range from 1 to 4 and can be x1, x2, p1, and p2. So again, yeah, just report the master equation. And then if we require that the gravity should be such that these dynamics should not entangle the state, that essentially this means that this gamma cannot be zero because these terms will tend to entangle. This should be larger enough to contrast efficiently the entangling effect of the Newtonian interaction, and a lower bound on this gamma parameter can be found imposing this PPT condition. We can do it essentially because here all the dynamic is Gaussian, so one can apply this. And essentially, so if gravity is classical in the sense it does not lead to any entangled state, then we found also including some symmetry assumption, but I would say very reasonable. Like we're supposed to have two masses which are the same, and if they are the same, then the decoherence acting on mass one should be same as the one acting on mass two in position and in momentum. So by doing some of these assumptions, we end up with this condition on the coefficient gamma 1 and gamma 3, so that this dynamics does not entangle the state. And if we look at the spectrum for these dynamics, and essentially we consider a regime where this eta is the damping, essentially is the friction effect. So we consider that this can be negligible. Then we see that the spectrum has the thermal term, which we added for including other possible environment, and the first term is exactly the same as the one in the bound. And so one can require, to be very conservative, one can just require that this should be larger than this. Actually, what we did was something a bit more elaborated, was to consider what happened if I cool down the system and then I study the reheating, and how the presence of this, given this bound, affect the reheating. And at the end, there was this possible I mean, the crucial point was that it was found that what mattered is the density of the masses, not their size. So you don't gain mass by using huge mass, but by using dense mass. And that the kind of quality factor that is required to be able to for this kind of test to work, I mean, it's still very high, is 10 to the power 10. I think currently now the limit is 10 to the power 6, but still this kind of test has the advantage that you don't need to put stuff in any superposition. Okay, and this is essentially a slide of conclusion. So I will go fast because I think I've been already over time. But what we show is essentially in Diósi Penrose model, you have this effect of spontaneous radiation emission, which can be used to to set a bound on the parameter of the model, and we set essentially this bound at 0 larger than 10 to the power minus 10 meter. On the other hand, if you require the model to collapse efficiently, you expect this at 0 also to be smaller than 10 to the power minus 2, so centimeter. And we have found that there is some interesting dependency of the spectrum um, from the model when you start to go to energy lower than gamma rays. Regarding the nature of gravity, well, if gravity is classical, then we expect that there should be some diffusive effect, which essentially must be there to ensure that entanglement is not generated. And so one can set a bound on this diffusive effect and search for this diffusion. And the logic is if you don't observe, if we don't find any of this diffusive effect strong enough, then gravity cannot be classical because it will generate entanglement. And I finish and thank you very much to everyone. Sorry if I was a bit over time.
Thank you, Sandro, for the very nice talk. Okay, so now we have time for questions. Please just unmute yourself and feel free to ask Sandro about his presentation.
Hello, may
Hello?
I?
Yeah.
Can you hear me?
Hello?
Can you hear me?
Yes.
Yes, okay. So just if I
Hello.
may start, I know if there's any order in. Okay, thank you for this talk. So I come from different communities, so I have two different questions. First, so I do experiment with cold atoms and light scattering, and we very often have a superposition of emitted light. So we have wavelengths of the order of microns, so invisible, so very low energy compared to
Yeah.
you. And this n squared scaling is something very common in our field. So it's super radiance. So this indistinguishable emission of emitters is something quite normal for us. So of course, if you would have a decoherence scheme which would make the emitters to be distinguishable from by any other means, that would break down. But this has been observed in many systems. So I don't know if this is putting any constraints on any of your models, but so in optics, invisible, it's a very common thing. This n square scaling is very common. So I don't know. I just don't know the numbers if this is interesting or not to put constraints. Okay,
Okay.
that's just.
Thank you. We'll check out.
Okay. Then the second question. Okay, so I also do experiments. So based on my optics experiments, I now go for astrophysics and do intensity correlation in astrophysics. And so actually, I want to probe probably the largest quantum object in the universe. So in size, I mean, not in mass. And this is not neutron stars, which are quite dense, but white dwarfs. White dwarfs are the size of the Earth, basically the mass of the Sun, and they are in a very degenerate. So this is a degenerate Fermi gas. And so and no one has seen could be able to measure the size. So we try to measure the size. That's one of the projects. But so I wonder. I already discussed this with other colleagues, but we don't know how to model this. If I have now these are fermions, so it's a little bit different. I know if you distinguish fermions and bosons, but you have a quantum system which has an extended wave function, and it's a many-body wave function. If there would be some decoherence mechanism inside, what effect would this have on the size of a Fermi gas, where the trapping potential is basically gravity, which pulls everything together? So I don't know if you could
Okay.
predict any effect of decoherence. So I was wondering about decoherence of gravitational waves, so a dynamic thing, not self. You have a different thing, right? It's a self collapse basically in your system. So it's not exactly the same which I had in mind, but I just wonder if you would have any, if you could apply your models on objects like such as white dwarfs, which are just the numbers are just astonishingly different from what we can do on Earth.
Oh, okay. So the honest answer is I don't know. But my guess, typically when you have this diffusive effect, the effect of collapse is to increase the diffusion. Then the reason why I say I don't know is because all this model works very well in non-relativistic framework, while in this kind of system, I think you're highly highly relativistic
No,
or
it depends.
oh,
Some
okay.
white dwarfs are in relativistic regime and some are not. There are different ones. So the one I want to measure is has relativistic corrections, but not
Hmm.
all. Not all of them have relativistic
Oh,
corrections.
okay. No, for the non-relativistic one can try to do some calculation. With the relativistic one, then
Yeah,
it's more delicate.
yeah, sure.
But in
So I
general,
just
what
want
I
to
expect
suggest that
is that
maybe,
the coherence should increase the
yeah.
diffusion.
I just wonder if you can apply all you do on either optics, visible regime for cold atoms, light scattering, and for white dwarfs where there's a very different numbers now. And if this collapse model could affect anything on dynamics of white dwarfs.
The
Sorry, can I interrupt you?
Sure, sure.
Sure, yes.
Yeah. However dangerous and strange is an extrapolation of our non-relativistic collapse models to the far relativistic objects. But it happens from time to time that we do. Some people do, and a quite recent one is a calculation of either heating or radiation in neutron stars. And the calculation was done. Sandro, you may remember Tilloy
Yeah, okay.
Tilloy
That was the
and
eating.
some
Mhm.
other, maybe senior. So
Yeah,
they calculated the bulk effect,
yes,
the non-interferometric effect of CSL and DP collapse theories inside a neutron star.
Ah,
So
yeah,
I don't remember exactly was that the heating that was mentioned by Sandro at the beginning of this talk,
yeah.
or
mm.
spontaneous radiation.
No, was the heating. Now I remember. They didn't compute radiation emission, but then the heating was compared to experimental data by looking at what radiation was emitted, but the calculation that they did was only about the heating, basically.
Yeah.
Yeah.
And so did they find any constraint on this? So, okay,
They
this was
found
interesting.
constraints which were good but not better than the one coming from this radiation experiment in Gran Sasso. They were fairly
Okay,
good. So
okay,
the overall idea, I mean, is good, but not enough somehow.
Yeah.
okay.
So,
I just, okay.
Unfortunately, it has nothing to do with optics.
No. This is different thing. This is not, yeah. Mm. Okay,
yeah.
thank you.
Thank you. Uh, okay.
Any more questions? Maybe in the meantime, I will ask one. So there are these two like indirect effect, the heating of the system and the
Mm.
radiation. But in
Yeah.
general, for the heating of the system, it's difficult to, even if you detect such a heating for a system, then it will be a bit difficult to infer that this is due to collapse, right? Because it
Yes.
could be some other source of noise that you might have not taken into account.
Yes. Yes.
So, by looking at the radiation, is this better in the sense that can you exclude other sources of noise for this emission of radiation, or the problem is still kind of there? And the fact that it's better is just better for more suitable for experiments for testing it.
No, I will say that the problem is still there. So then that slide that I show where we discuss what happened when you consider energies uh, a bit lower than gamma ray, when you have emission of radiation which strongly depend on the model. That may help a bit in that direction, but overall, and this is a general issue of this collapse model that they predict some noise, but when you see some effect, you can never say for sure this is due to the collapse. First of all, I think you should first of all find an experiment where you can be sure that there is some noise which you cannot explain in any other ways. But then you have to think about many other experiments. I will say to cross check that essentially all this effect can be explained properly by this collapse model. I'm just thinking.
Because
But still, you may have in principle some other decoherence model which acts in a very similar way. But I mean, it
because you have one more
depends.
constraint, no? Like the
Yeah.
frequency range of the emission. Because if it's too
But
as
that will happen. No, yeah, but that will happen even if you have even if the noise was not coming from collapse, but from something else. You will still have all the discussion I did about coherent or not coherent emission depending on the distance. That will be true even for these other
other
uh,
source of noise that
models. No, the thing changes slightly when you start to go in that range where the wavelength is comparable to the atomic size, essentially. Because if you take the wavelength much smaller, like we did until now, with gamma rays, so of order of 10 to the power minus 12 meter, then the emission essentially is always coherent from nuclei and coherent from electron, full stop. If you take a too large wavelength, uh, essentially the effect is zero because the emission cancel perfectly. You see something in this range in between, and that might depend strongly on the form of your Lindbladian, which means on your collapse mechanism. Uh, so that may be more useful. Then, yeah, you still, I mean, when you detect some signal before telling this is a collapse model, then I want to see the same signal coming from many other experiments and where nothing else can explain it. And in general, I would say it's very much harder to confirm collapse model, which is the reason why typically what you do is to set bound, because that you can always do. Uh, I think it would be nice if one can find some prediction and some way also to introduce a collapse model which is a bit less phenomenological and then which leads to some very characteristic prediction, which I don't know, some spectrum with some peak at some precise energy that you say, okay, this is exactly.
with some feature or some characteristic
Yeah.
that
But I
is
think this is more work that should be done theoretically. This is my feeling, at least.
okay.
I don't know, Lajos, what. Yeah.
Yes, that's. I think that's the basic genetic problem of the people in the laboratories. That the background noise is always there, and the major war is against the background. So that's why we went down to the Gran Sasso, a deep isolated laboratory to suppress the environment, the environmental noise. But it is always there, and we detected some gammas from apparently from the remainder of the cosmic radiation, cosmic and other radiative processes in the rock of Gran Sasso. So the task is to get a signal which is a bit above the background. And as Sandro was explaining, if we have some chance to see some structure, either of the background, which is usually quite flat, or we see some structure or some parameter dependence, characteristic parameter dependence of the predicted new effect of collapse, then we are done. But we are not yet there.
Yeah, thanks. There is a question in the chat.
Yeah.
I'll read it. So, are you familiar with the recent PRD by David Trillo and Michael Navasquez that shows the DPD model actually predicts entanglement in the BMV setup for some values of the parameters? And also, any comment on relativistic extensions of the models? Could possibly different predictions stem from them and offer more possible experiments?
Okay. Okay, in order, on the paper of David Trillo and Miguel Navascus, sorry, I'm not sure I pronounce it well, is I didn't read it in detail, but I'm familiar a bit. I knew that there was this result. I think in that case is the reason why you get this entanglement generation in the DP model uh, is that I think somehow because you have the correlation of the noise, which goes as 1 over x, I think essentially the model is okay. I may be wrong, but in case you can correct me, but Lajos, but I think the assumption that is lost is locality. So because if it is an LOCC would have not generated entanglement. If I remember, is the locality and is due because I can see the DP model as doing measurement which are somehow not point-like but extended on some region given by this at zero, and this somehow introduce some form of non-locality.
Yeah.
But I have
Sandro,
no.
I wanted to raise my hands, but I didn't find the.
Please go ahead because probably you can answer
So
better than me.
I supported the Novasquez invention or finding, and they are absolutely correct. Not necessarily in the interpretation of the result, but in fact, you are right. Your answer was correct that mathematically the very, very suppressed entanglement effect of the otherwise local DP model is related to the correlation of the noise. But the best explanation needs an alternative but very important reinterpretation of the collapse models. The collapse models can be interpreted in terms of our standard knowledge on measurement. So the spontaneous collapse is the same as standard collapse, which follows the standard measurement. Our measurements are technically, mathematically the same as standard measurements, but without the assumption of the measuring devices, the observers, and so on. So the nice interpretation of collapse models, whatever they are, CSL or DP or GRW, the first one, the historic one, is the following, that we assume that in nature measurements are spontaneous, without the conscious beings, without measuring devices. So measurements happen in nature universally, everywhere, every time, at a very, very weak way. And this is the reason for spontaneous collapse.
Okay.
And if you take this interpretation of spontaneous collapse theories, which are my favorite interpretations, then you understand that in case of CSL or in case of DP, the measurements are non-local. And they are non-local because local measurements are divergent. And the cutoff parameter, the smearing parameter are not in dp. It's just the size, the characteristic size of the domain of a single non-local measurement, spontaneous measurement, which happens everywhere, every time by the overmighty or by the big brother. So the dp measurements, spontaneous measurements, are non-local, and the non-local measurement generates entanglement.
Yeah.
This is the basic thing to understand, that local measurements do not create measurement between different parts, between separate parts. But if the measurement is non-local, and the non-locality of dp is quite strong, because the decay is 1 over r.
Yeah.
Okay. Yeah.
Yeah. And with respect to the second question about relativistic extension of the model and possible different prediction, well, for sure there will be different prediction, of course, because the model will change. On the relativistic extension, again, I mean, I can say something, but really, Lajos is much more expert than me on this. But from what I know, is in general not easy, and the main reason is that this heating mechanism, the one responsible also for radiation emission, tend to become divergent if you when you try to naively extend the non-relativistic collapse model to collapse mod to relativistic one, essentially because you have a delta in time, and then to have a delta in space, I suppose you should have also this R naught or RC that goes to zero, but then you can see immediately that this will lead to explosion of energy and other stuff. Uh, but there are ways to solve this, but honestly, I'm not expert enough to say much. And the model which have been put forward, as far as I know, they mostly work only for free particle, non-interacting, and but I don't know. Again, Lajos, if you want to add something, feel free because you are more
Yeah,
expert. Uh,
I wouldn't mind,
hmm,
because I have quite a strong position regarding the relativistic extension or generalization of spontaneous collapse models. And again, my judgment and sentence and opinion are in terms of my favorite interpretation. The spontaneous collapse is just like standard collapse, because spontaneous measurement is just standard measurement. And of course, not the projective standard measurement. By standard measurement, I mean the generalized weak or time continuous measurements, which are standard because they're part of standard quantum mechanics. You can generalize von Neumann measurements for time continuous, not projective, POVM-like measurements. Okay, so the bottleneck is that we have wonderful mathematics and theory and interpretation for Markovian Markovian time continuous measurements, but we don't have any universal relativistic time continuous theory of measurement. And the obstacles are basic, and these obstacles were, for instance, characterized by Weismann, who didn't do too much work or didn't do any work in the spontaneous collapse context, but he knows why non-Markovian measurements, I mean measurements with memory, are very, very different from the Markovian special case. The Markovian special case is there in any modern quantum optics lab where so-called homodyne detections are exercised in every night and day, but they are typically, since they are Markovian, they are not relativistic. Non-Markovian stuff needs memory measurements with memory, with coherent quantum memory, and these class of measurements are very, very difficult, and we don't really understand them. And in my opinion, this is the bottleneck, that the basically memoryless Markovian theories of spontaneous collapse, GRW, CSL, DP, are resistant to relativistic generalization. This is my position.
Okay.
Okay, thanks. Are there any other questions? We
Yeah,
have time for discussion also after.
Yeah, also just one more comment about this relativistic extension, but this is more like an opinion, not honestly. If I never tried to attack this problem, I think it's very hard. But I think one way I would like to start to think about this is by doing some simple sort of Gedanken experiment, like taking a model like GLW where the collapse is this given by with this rate lambda. And for example, if I'm in a relativistic framework, then this rate of localization should depend on the observer, whether is moving with a certain velocity, then the number of rate should also change, and then this in theory should also lead to different heating depending on which inertial observer I'm considering. So I don't know. I may be also wrong in what I just said, but overall, my feeling is that I think it would be interesting to do this kind of Gedanken experiment without writing down too many equations, but more to get
Yeah.
an intuition.
Yeah, exactly so. And here we must at least mention Tumulca's works, Roderick Tumulca's works, who started from the GRW, the elementary model, to construct some kind of relativistic extension. And also Philip Pearl, who's even older than me. So we must respect his contribution. He created the first relativistic extensions of the CSL model, but they are divergent. They are problematic. So.
Okay. So.
Okay. So I will stop the recording now.
Okay.
Thank you again, Sandro.